Okay, so here we're going to look at the difference between refraction and diffraction. So refraction is the bending of light as it goes from one medium to another. So if we're going from air through glass, from water through oil, it's going from one medium into a new medium. And Newton was able to refract white light, and what he saw was that red is refracted the least and violet is refracted the most based on their wavelength. Okay, so the longer the wavelength, the lower or the least amount of bending you're going to see. The shorter the wavelength, the more bending you're going to see. So that's why red looks like it's just coming out almost parallel, and violet is substantially bent. Okay? So refraction explains our rainbows, and because it's not moisture, it's moisture. There's the moisture in the air acts like prisms. So the water droplets in the air all together collectively act like one huge large prism, and it disperses the white light. So dispersion is a new word that we're looking at, and it separates the wavelengths into individual wavelengths, or the one big wavelength into their individual wavelengths. White light, as we know, is made up of a bunch of different wavelengths, and so each one has a different angle of refraction. Okay? Shorter wavelengths, we already talked about this, bend the most, and longer wavelengths refract the least. Okay? The spectrum produced by refraction is the opposite of the spectrum produced by diffraction, in the sense that the shorter wavelength diffracts the least and the longer wavelengths diffract the most. Okay, because here, if you're just looking at this and you say the spectrum produced by a refraction, because we get red, orange, yellow, green, blue, indigo, and violet, this is the longest wavelength, this is the shortest wavelength, this bends the least, this bends the most. Well, over here for diffraction, we still see Roy G. Biv, we still see red, orange, yellow, green, blue, indigo, violet. We still see the colors in that same pattern, but what we're seeing here is that this least amount of bend here is violet. So here, the short wavelengths diffract less. And the longer wavelengths diffract greatest. So that's where the difference is. The color pattern is still the same, but here a long wavelength bends the least and a shorter wavelength bends the most, or refracts the most, if we want to use the correct word. Okay, so this is important that you understand this part of it when it comes to diffraction. Polarization. Shay wears glasses, but I don't know that hers change color in the sunlight. So polarization supports wave model for electromagnetic radiation, and that EMR is a transverse wave. Okay, so polarized wave vibrates only in one direction. So either only in the electric field direction or only in the magnetic component direction. Non-polarized light vibrates in both directions. And so EMR waves have both electric and magnetic components. But what's being polarized is only one of them. So it's possible that you filter it all out. So what you do is, here's your light beam or your incident beam coming in, and you have a polarizer that's going to only look at waves that are going in this direction. So we have this direction, and then we also are going to have these other ones here that are going to go in behind and come back out. Okay? And then, because light is not just nice, neat, and tidy, we have these ones that, if you could see, come down. Okay? But because the polarizer is oriented in this direction, only these waves going up and down are going to get through. It held on to all of the other wavelengths. Then if we take a polarizer and we rotate it 90 degrees, so these are going this way, and the second one is going this way, they're 90 degrees. Now we have no light coming through. So polarized lenses in glasses work on this exact same principle. Only instead of being 90 degrees, which would totally suck, you wouldn't be able to see anything, maybe they're like this. And it limits the light passing through. You will see a polarization question on the diploma, I guarantee it. Okay? So, every polarizing filter has a polarizing axis that only allows light to pass through, that's vibrating in that same plane. Same plane as the orientation. Okay? So the fact that EMR can be polarized proves that EMR is a transverse wave. So transverse means that it's going perpendicular to the wave oscillation. Okay? So if we have waves moving in this direction, we can have a wave going like this. Okay? So if you place polarizing filters perpendicular to the way that it's going, it allows them to eliminate that vibration or the oscillation. All right, practice problem. There are questions at the bottom of the other page, but I'm tired of fighting with my smartboard. See? Ta-da. All right. Describe two methods to separate dispersed white light into all of its wavelengths. Compare the spectra that are produced from each method. So how can we separate or disperse white light? One, we can use a prism, correct? So each wavelength you'll need to recall what Snell's law is, the whole line, okay? And then a second method would be what we just learned, would be to shine the white light through a diffraction grating. Okay? And so then what we see there is that each different wavelength will be diffracted differently. Will be diffracted at a different angle, and here, based on okay? And so if you need to compare, you can compare the rainbow spectrum here and refracted versus wavelength there. And here you can look at the same rainbow or a monochromatic light. Through a grating. And you can look at diffracted angles versus wavelengths. All right? So as wavelength increases, the value of sine theta increases. All right. That's good. Make sure you get those 2 sets of questions done. We have 1, 2, make that 3, 4, 5 classes left in this unit. Ooh, what are the odds that we can tie it up before Christmas? Depends how motivated you guys are. Have a great weekend.